Hello and welcome to Video Podcast 11.4. In this video, we will overview atmospheric heating. I'd like to start off by talking about the difference between heat and temperature, because those are often confused terms. For our purposes in this course, when we say the word heat, we are talking about thermal energy. And more specifically, heat is the energy possessed by a material that arises from the internal motions of atoms and molecules. Another very important thing to keep in mind that will always be true is that heat is always transferred from warmer objects to cooler objects. I use this as an example, and I don't want you to try it at home, but if you put your hand on a burning hot stove, the stove will transfer energy to your hand because your hand would be cooler than the stovetop. So in terms of heat energy, the heat energy is flowing from the hot stovetop to your cooler hand, and that's what causes you to get a burn. Now, temperature is different. Temperature is the quantitative measure of the intensity or the degree of quote-unquote hotness. At the molecular level, what temperature is basically measuring is the average motion of atoms or molecules within a substance. In terms of measuring temperature, scientists use the Celsius scale, although you're probably most familiar with the Fahrenheit scale. In this course, I will reference both scales, just make sure you pay attention to which unit we're using. Now let's overview the three mechanisms for heat transfer. The first one I'd like to start with is conduction. And you're probably familiar with this one if you've ever grabbed the handle of a pan that had boiling water in it and you noticed that it was hot. Shown on the screen is a little GIF image that should help you conceptualize how conduction occurs. Basically, you have some warm atoms and they're jiggling very rapidly, and that rapid jiggling will cause the atoms next to them to kind of gain that heat energy and start to jiggle rapidly as well. So essentially, conduction is the spreading of heat energy through molecular activity. The second heat transfer mechanism is one that you should be familiar with by now because we've referenced it many times, and that's convection. Convection is the mass movement within a substance. If you take a look at the picture of boiling water, we actually have conduction occurring at the very bottom of the pan. The metal bottom of the pan is extremely hot, and through conduction, the hot bottom of that metal pan will transfer heat energy to water molecules at the very bottom of the pan. When water at the bottom of the pan gets warm, it will expand. And when that expansion occurs, the water at the bottom of the pan will be less dense than the water near the top of the pan. Consequentially, that less dense water at the bottom of the pan will rise to the top, and the cooler water at the top of the pan will cycle down towards the bottom. Once that cooler water gets to the bottom, it will absorb heat energy, and that cycle will continue as long as heat energy is being provided to the bottom of the pan. The third and final mechanism for heat transfer is radiation. And when we use the term radiation, we're talking specifically about electromagnetic radiation, which I will overview on the next slide. Okay, at this point I'd like to elaborate on radiation. Radiation doesn't need a medium to travel through, meaning that radiation will have no problem traveling through outer space. It's also important to note that all electromagnetic radiation travels at the exact same speed, and that's about 300,000 kilometers per hour or 186,000 miles per hour. Very obviously, electromagnetic radiation travels at a very high speed. Now, before taking a look at the electromagnetic spectrum, which is shown on this slide and a very important consideration in this class, I'd like to talk about some of the laws of radiation. One of the first things that we always have to keep in mind is that all objects emit radiant energy, including you and me. Another important consideration is that hotter objects will radiate more total energy per unit area than cooler objects. And along those same lines, hotter objects will radiate more short wavelength radiation than cooler objects. And lastly, good absorbers of radiation will also be good emitters as well. Okay, let's shift our attention to the electromagnetic spectrum shown on this slide. Now at the far left, we see gamma rays. Gamma rays will have the highest energy of all electromagnetic waves, and they will also have the shortest wavelength. Okay, let's look at visible light because that's what we're most familiar with. Of all the types of electromagnetic radiation shown, visible light is the only radiation that we're capable of seeing. If we focus just on the band of color shown at the top of the slide, the most energetic type of visible light is violet light, and the least energetic of visible light is red. Now maybe at some point in like a high school science class, you learned Roy G. Biv, and that helps us organize the colors from low energy to high energy. Roy G. Biv would be read backwards on this particular image, because we have the higher energy electromagnetic radiation to the left side and the lower energy electromagnetic radiation to the right side. Now hopefully this is kind of common sense, but with violet being the most energetic of the visible lights, just outside of the violet range is ultraviolet. And ultraviolet radiation is more energetic than the most energetic visible light. Our eyes can't see ultraviolet light, because anytime we get to wavelengths that are shorter than violet light, it's invisible to us. Now let's go to the other end of the visible light spectrum. Of all the colors of visible light, red light will have the longest wavelength and the lowest energy. Now if you go just beyond red light, you reach infrared. And just as our eyes cannot detect ultraviolet light, our eyes cannot detect infrared light either. Red light is the longest wavelength that our eyes are capable of seeing, and any electromagnetic radiation that has wavelengths longer than red light will be invisible to us. So that means we cannot see infrared, we can't see microwaves, and we cannot see radio waves. And of course, to the left side of the visible light spectrum, we cannot see ultraviolet light, we cannot see X-rays, and we cannot see gamma rays. We have technologies and equipment that are capable of seeing all of these different types of electromagnetic radiation, but our eyes are kind of limited in what they're capable of detecting. Our last consideration in this video podcast is heating the atmosphere. And while we're on the topic of radiation, we're going to focus on solar radiation, which is electromagnetic energy coming from the sun. Now, our atmosphere is capable of doing three different things with that incoming solar radiation. It can reflect it, it can scatter it, or it can absorb it. And Earth's surface can either reflect or absorb that same solar radiation. Let's start off by considering the difference between reflection and scattering. Reflection is when light bounces back from an object at the same angle it was received without absorbing or scattering. We have an intuitive understanding of reflection because every time we look in a mirror, we're seeing the concept of reflection in action. Now, scattering is a little different than reflection. Aerosols and gas particles in our atmosphere are capable of scattering electromagnetic energy in all directions. The final atmospheric effect we have to talk about is absorption. With absorption, if a gas molecule in our atmosphere absorbs electromagnetic energy, that energy will be transformed into internal molecular motion, and we would detect that as an increase in temperature. The center image helps us conceptualize how much of the incoming solar radiation is reflected, scattered, and absorbed. Our primary consideration is the source of the electromagnetic radiation, and that's the sun. Of all of the incoming solar radiation, about 5% will be scattered back into space by our atmosphere. About 20% of that incoming solar radiation will be reflected off of clouds and sent back to space, and about 20% of that incoming solar radiation will be absorbed by the atmosphere and clouds. Now, some of that solar radiation will make it to Earth's surface. In fact, about 50% of the solar energy that enters our atmosphere will be absorbed by the land and sea. About 5% of that incoming solar radiation will be reflected from the land and sea. So let's do a little bit of bookkeeping at this point. Of all of the solar radiation that enters Earth's atmosphere, about half of it will be absorbed by the land and the sea. About 30% will be lost back to outer space by reflection and scattering, and about 20% of that incoming solar radiation will be absorbed by the atmosphere and clouds. Okay, our final consideration in this vodcast will be the picture you see to the far right of this slide. A term I would like you to get familiar with is albedo. And albedo is essentially the percentage of electromagnetic energy that will be reflected. Now, it's important to note that different surfaces are more or less reflective than other surfaces. As an example, asphalt has a very low albedo, meaning that when solar radiation strikes asphalt, most of that solar radiation is going to be absorbed by the asphalt. And you might have experience with this, because if you've ever been outside on a hot, sunny day and felt asphalt, you know that asphalt can heat up rapidly. Now, on the flip side of the coin, snow and thick clouds are very good reflectors of incoming solar radiation, and they both have very high albedos. One of the problems with climate change is that ice and glaciers are really good at reflecting solar energy back into space, but as our ice and glaciers continue to melt at accelerated rates, we're seeing a much smaller percentage of Earth's surface that's effective at reflecting solar energy back into space. Very obviously, feel free to pause at any point and kind of study these images in detail, and hopefully the concepts are starting to kind of click. But at this point, this is the end of Vodcast 11.4. In our next Vodcast, we're going to focus on some of the factors that affect worldwide climates and worldwide temperature distributions. And we also still have a very important Vodcast upcoming, and that's regarding climate change.